Hello everyone. In this tutorial, we will cover planes in space. Last week, we talked about lines in space. Particularly, we talked about parametric and non-parametric equations for a line. We talked about relative position between two lines, and also we talked about the distance between a point and a line. In this tutorial, we will cover planes in space. Particularly, we will talk about general equations of a plane, equations of a plane passing through 3 points, other forms of equations of a plane, angle between two planes, distance from a point to a plane, relative position of planes, and finally relative position of a plane and a line. So let's start with a brief talk about general equation of a plane. The general equation of a plane in a Cartesian coordinate system has the following form: ax plus by plus cz plus d equals to 0, where x, y, and z are coordinates of a point in the plane. Let's assume that we have a point M1 inside the plane. So by inserting the coordinates of the point into the equation of the plane, so we reach to the equation as you see here. Subtracting the equation number 2 from equation number 1, we obtain another form of general equation of a plane, as you can see here. Assume that A, B, C are the coordinates of some vector n. So the left hand side of the equation 3, as you can see here, is a scalar product of vector n and the difference radius vectors r minus r1. So we can rewrite equation number 3 as a scalar product of vector n and r minus r1. So we can see here, as illustrated in the this photo, by the properties of the scalar product, this equality implies that vector n is perpendicular to the vector r minus r1. And since r minus r1 is an arbitrary vector in plane P, so n is a normal vector to the plane P. So from equation 3 we can say that a plane that passes through the point M1, the coefficients A, B, C can be interpreted as the coordinates of a normal vector to the plane. So if you have an equation like this, simply you can say that A, B, C are normal vector of plane P. So let's consider a few particular cases of general equation of plane. So if we have a d equals to 0, then the equation will be something like this: ax plus by plus cz equals to 0. This plane passes through the origin. If c is 0, then we have this equation, and which means that the plane is parallel to the z-axis. If b is equal to 0, in this case the plane is parallel to the y-axis. And if a is 0, so the plane is parallel to the x-axis. If a and b equals to 0, so the plane is parallel to the xy plane, and the plane is perpendicular to the z-axis. There are also the other two forms. You can find it by yourself. If a and c become 0, what does it mean? Or if b and c are zeros. So think about it and write your expressions. Let's have some examples here. Let point M1 be a point in a plane and n be a normal vector to the plane. determine the equation of the plane. So in this case, from equation 3, from the general equation of the plane, we have coefficients that are described by n, and we have a point. So we have x1, y1, z1. So simply we have to insert these points, the coordinates of points and coordinates of normal vector inside this expression. So by inserting, we reach to the equation of the plane. Another example here. A plane is given by the equation x minus 2y plus 3z minus 6 equal to 0. Find a unit normal vector u to the plane. So first we need to find the normal vector to the plane and then calculate the magnitude of the normal vector, and then we can find the unit normal vector. So in this case, so from the equation we know that the coefficients of x, coefficients of y and z are the normal vectors. So we have 1, minus 2 and 3. 1, minus 2 and 3. So this is our normal vector to the plane. So the magnitude of the vector, you can say that the square root of the summation of these components power 2. So we have a square root of 14. This is the magnitude of the normal vector. So we can say that unit normal vector u is a vector n divided by its magnitude. So we have the unit normal vector u. Find any 2 points in the plane. So we have equation of plane and we want to find any 2 points. So simply you can set any numbers to x and y and obtain z, or vice versa. For example, here I set the easiest one, which is a x and y equal to 0. So we obtain z as a 2, just inserting here. And for the second one, we can say that x and z equals to 0. Then we can calculate y from the equation of the plane, so which is minus 3. So we can say that m1 with the coordinate 0, 0, 2 and m2 with the 0, minus 3, 0 are the points in the given plane. Now let's have a talk about equation of a plane passing through 3 points. Let 3 points m1, m2 and m3 be 3 given points in a plane, and m be an arbitrary point in P. So we have 3 vectors m1 and m1, m2, m1 and m3. So simply it's r minus r1, r2 minus r1, r3 minus r1. We know that these are 3 vectors. All of them are lie in the plane P. So you know it from the scalar triple product. So their scalar triple product should be 0. So when we have a scalar triple product, we can rewrite it in the determinant format as we have it here. So this equation describes a plane passing through 3 given points. So if in example or something they ask you to find the equation of a plane passing through 3 given points, so simply you can use this determinant. Let's have an example here. For example, we have 3 points m1, m2, m3 be points in a plane, and we want to find an equation of that plane. So we use that determinant that I showed you in the previous slide. So we have x minus x1, x2 minus x1, x3 minus x1. So and the other components here, I wrote it here. And now we have to calculate these determinants, and you know how to do it. So it's like, for example, this one times by minus 8, we have it here, and y minus 5 times by 8, and z plus 1 times by minus 8 times 2, so which is plus 16. So from here we can expand it, and we reach to the equation of the plane, which passes through these 3 points. The other forms of equations of plane, assume that we have a general equation of a plane in this format. So in this case, if we simply set y and z to the 0, so x will be a. If we set x and z to 0, y will be b. X and y be 0, so z will be c. Therefore, the quantities a, b, c are respectively their x-intercept, y-intercept, and the z-intercept of the plane. Also, this equation is called the equation of a plane in the intercept form. This equation. For instance, for example, if we have this expression x by 2 plus y minus 5 z over 4 equals to the 1, describes the plane with the x, y, and z intercepts 2, minus 5, and 4. Let's have an example here. Find the equation of a plane which passes through point M1 with these coordinates and orthogonal to the line given by this equation. So the equation of the line, we talked about it last week. So just recall it from that tutorial. The direction vector of the line is the normal vector to the plane, because here we wanted to find the equation of plane that is orthogonal to the line P. So the direction vector of P is our normal vector. So here the direction vector of line, as you remember, is this one. So we have a parameter, and after that we have a normal direction vector. So this direction vector is a normal vector to the plane, so which is a 2, 1, minus 3. And we have a R1, so we have a point on the plane. So the position vector of M1 simply is 5, 4, minus 8. From slide 4, as you remember, we obtain the equation for a plane. So in this case, what we have? So we have R minus R1 dot n equals to the 0. So R is the position vector of any 1 point on in the plane, and the normal vector, and R is the position of arbitrary point on the plane. So in this case, just we have to insert here, and we should calculate this equality, and this leads to the equation of a plane which passes through M1 and it is orthogonal to line P. Here we want to talk about angle between two planes. The angle between two planes, theta, is the angle between their normal vectors n and m. So we have two vectors and we want to find the angle between them, so we can use the dot product of two vectors. If the planes are given by the equation general form a1 x plus blah 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 equal to 0, a2 x plus b2y equals to 0. So from here we know that this is the a1, b1, c1 is the normal vector of one plane, a2, b2, c2 is the normal vector of the other plane. So we can insert them in this expression here. So we can rewrite cosine of theta as the dot product of m over the magnitude of n times by the magnitude of m. If two planes are perpendicular to each other, so which means that the denominator will be 0. And if they are parallel to each other, which means that the normal vectors n and m are proportional to each other. So note that the vector product of non-parallel vectors in plane gives a normal vector to the plane. So we know it from the product vector product of two vectors. In particular, if a plane is given by 3 points, so we have m1, m2, and m3 is given, then a normal vector to the plane is the product of these two vectors. So we can use this determinant to calculate the normal vector of a plane, and by having 3 points on that plane. Let's have an example here. We want to find the angle between two planes, P1 and P2, if P1 passes through the points M1, M2, and M3, and P2 is given by the equation 3x minus 4y plus z plus 5 equal to 0. So we know that to find the angle between two planes, we need to find the angle between two normal vectors. So for the P1, which pass through 3 points, to find the normal vector, we use the determinant from the previous slide. So here we have ijk and 2, 3, 1. How we can find 2 is a 0 minus 2, 3 is a 5 minus 2, and 1 here is a 3 minus 2. And from the last row, for the last row we have a x3 minus x1. 1 is 3 minus 2, and 2 is a 4 minus 2. So we have a from here we have a normal vector to the plane P1. For the plane P2, so we have a coefficients of x, y, and z are the normal vector to the plane P2. So we have a 3 minus 4 and 1. So we have two vectors, and we need to find the angle between these two vectors. We use the cosine of theta, the dot product actually. So cosine of theta will be 11 over the square root of 130, and we do arc cosine of this value leads to the theta, which is around 16 degrees. Distance from a point to a plane. Assume that a plane P determined by the following equation. So we have a general form of plane P, and point Q is not in the plane, and we have a M, which is an arbitrary point in the plane P. So we have a point, arbitrary point on the plane, and we have a point which is not in the plane. The distance D between the point Q and P is equal to the absolute value of the projection of OM on the N normal vector. So for details of this, we did it for the line in the previous tutorial. So here we have it for the distance from a point to a plane. So equation 6, from here we have the ax, so we just rewrite it in this format: ax plus by plus cz equals to the minus d, and we can find this formula for the distance from a point to a plane. For details, you can go to the tutorial 6, the previous tutorial, and there are details how we can reach to this formula. So let's use this formula. Find the distance from the point Q to the plane given by the equation as here. So we use the formula from the previous slide. We have ax1 plus by1, and we need to find the absolute value. So we have a, b, c, and we have x1, y1, and z1. Simply we insert it to this equation, and we can calculate the distance from a point Q to the plane P. Relative position of planes. Here we have two planes are given by the general equation first. So for P1 and P2 we have general equations. Now consider them as a system of two linear equations. So let's see this, several cases. If system 7, this system, is inconsistent, as you remember, it means that there is no solution for that. Then we can say that the planes are parallel, and so the coordinates of the normal vectors n1 and n2, so a1, b1, c1, and a2, b2, c2, are proportional. So these parts are proportional. So these planes are parallel. And pay attention, d1 and d2 are not proportional. I mean this inequality here. And because of this, the system is inconsistent. But if the system is consistent and the equations are proportional to each other, so here, as you can see, fully proportional to each other. In this case, P1 is just the same plane as P2, so they are one plane. In the last case, if the system is consistent and the rank of coefficient matrix equals 2, which means that we have a full rank matrix, then planes P1 and P2 are intersecting planes. The locus of this distinct intersecting plane is exactly one line. The vector product of two normal vectors to the plane P1 and P2 is a vector which is perpendicular to the normal vectors, and so it lies in both planes. Therefore, the vector product of these two normal vectors is a direction vector L of the intersection line L. So if you want to find the intersection line, so you can find the direction vector of it by the vector product of two normal vectors. Let's have an example here. Suppose that we have two planes with equations that you can see here. We want to find all points which satisfy both equations. In this case, we can write these two equations as a system of linear equations, and we need to solve them to find x1, x2, and x3. So in this case, we need first step is that to get rid of x1 from the second equation. So how we can do it is subtracting the first equation 2 times from the second equation. We reach to the new second equation, and we can divide it by -3, so we have a new second equation, x2 plus x3 equals to 2. From here we can write x2 as a function of x3, and we can substitute it here. Then we can say that x1 as a function of x3. So let's have some calculation here, and we reach to the expressions for x1 and x2 in the terms of x3. So we can say that if we assign, for example, lambda to x3, we can write the equation of a line, which is the intersection line of two planes. So this line has a direction vector of 3, -1, and 1. So let's have another example here. State the relative position. Are they coincident, parallel, or intersecting of the following planes? So we have a system for two planes. So we want to find their relative positions. So here, as you can see, that we know that we have a normal vectors for plane 1, which is 1 and 2, and for the second one is a -2 and -4. So we have these proportional and inequalities. From here we can say that the planes are parallel because the system is inconsistent. Let's have another example. Here we have two planes which are given by two equations, as you can see here. In this case, again, we need to write the system of linear equations and solve it. So system is consistent, so there's a solution for that, and we can see that the normal vectors and coefficients are proportional to each other. So as you remembered, when we have a proportional coefficients and the system is consistent, then P1 is just the same plane as P2. Here in this part, we will consider the relative position of a plane and a line. So let be a plane A be given by this general form, and line be determined by the system of two linear equations, as you can see here. So to investigate the relative position of the line and plane, so we integrated these two systems in one system of equations. So we have three possible cases. First, if the system, the coefficients matrix equals 3, the rank of it, then the system is consistent and has a unique solution. It means that this unique solution is the point of intersection of the plane and the line. The other cases, if the system is consistent, but the rank of coefficient matrix equals 2, then line L lies in the plane P. And in the last scenario, if system is inconsistent, so there is no solution, it means that the line L is parallel to plane P. Let's have some example here. We want to state the relative position of the line and plane. So we have equation of plane and equation of the line. In this case, we have a coefficient matrix, as you can see here. So we have a 1, 1, 1, minus 1, 1, 1, 1, minus 1, and you can do it for the other equations as well. So this coefficient matrix is our system, so you can solve it by yourself, and you should reach to this one. System is consistent and the rank of the coefficient matrix equals 2, which means that the line L lies in the plane P. So home, you do it by yourself. Calculate this system and find out that you should conclude that the system is consistent and rank equals to 2. The other example here, we have a plane and line which determined by these two equations. So we construct the coefficient matrix. This system is consistent, which means that there is a solution, and the rank of coefficient matrix equals to 3, which means that we have a full rank matrix. Then the plane and line have an intersection point. So this is somehow assignment for you. Find that intersection point. So in the last part, we have an angle between a plane and a line. So let alpha, this is alpha. Angle between a normal vector to the plane and the direction vector L of the line. And beta is the angle between the plane and the line. So from here you can see that the alpha and beta are complementary angles. So alpha plus beta equals to 90 degrees. And from here we can write these expressions using the dot product of two vectors, normal vector to the plane and the direction vector of a line. Let's have an example here. We want to compute the angle between the line L with the parametric equation. So we have a parametric equation of a line and the plane U with the general equation here. So we need to find the direction vector, normal vector, and using the dot product. So the direction vector of the line is here, 0, 1, 1. And for the normal vector to the plane is 1, 1, and 2. So we can write the expression here. So according to this expression, alpha is 30 and beta is 60. So next week we will talk about new topic, which is quadratic curves. So see you in a question answer section, and good luck.